All right. So now let us begin with the last chapter of 11th, that is waves. Okay. So what is a wave? It's a disturbance that travels in a medium without moving particles of medium. This is definition. Okay. Without moving particles of medium from one place to another, and disturbance carries energy and momentum. Okay. So what is this wave? So suppose you have a string, and one end of the string, okay, so suppose you have a string, one end of that string is held by you and another end you pass it to your friend, and suppose then you oscillate it. Okay, so now suppose you oscillate that string, then what happens, this kind of wave travels along the string, right? So this thing is known as wave. What's happening? Is the string moving from you to your friend? One end is held by you, another end is held by your friend, suppose. Okay, you hold one end, your friend holds another end. Okay, now does the string move from you to your friend? No. What moves? This wave moves, right? Okay, so wave is formed at one end and it travels to the other end. And what happens actually, you have started, so you displace the string upwards or downwards, so you are displacing the particles at this place only, upwards or downwards, right? And the wave is propagating like this. Okay, so displacement of particles is like this and wave is propagating like this. That means displacement is along y axis, you can say, and wave propagates along x axis. So this kind of wave is known as a transverse wave. Transverse means perpendicular. Okay, all right. So now the particles of medium are not carried by the wave. So as I said, the string, in the string, the particles from here don't move at the other end. What happens is only the wave is moving. That means the particle at this place are, they start displacing. Okay, they start actually oscillating up and down. So their energy and their momentum, it will move to the other end, and particles at this end will also start moving up and down. So we say that the wave is moving. Okay, all right. So this is just some introduction. Then we have types of waves. So what are the different types of waves? First one is mechanical waves, second one is electromagnetic waves, and third one is matter waves. So now what are mechanical waves? So the waves which require a material medium, okay, medium which is filled with matter, right? It is known as material medium. So these are called as mechanical waves. Okay, so the waves which require material medium for their propagation is known as mechanical waves. Then the waves which do not require any medium for the propagation, they are known as electromagnetic waves. Okay, so the examples of mechanical waves are sound waves, then waves formed on the string, then waves formed on the surface of water. Okay, right? So these are all mechanical waves. Sound waves, then waves formed on a string, waves formed on the surface of water. Then what are electromagnetic waves? So electromagnetic waves, there is a separate chapter called electromagnetic waves in 12th, right? So some examples are light. So visible light is electromagnetic waves, then microwaves, then electromagnetic waves used for communication. So these are called as radio waves. Okay, so these are all examples of electromagnetic waves. And then there is third category of waves, which is known as matter waves. So this thing, we'll talk about this later, but just for now, if a particle moves with momentum p, then there is a wave associated with that particle too, and that wavelength of that wave is given by h by p, where h is called as the Planck's constant. Okay, so we'll talk about this in the dual nature of radiation and matter, right? So in this chapter, we are going to talk about the mechanical waves only. Okay, so then let's talk about mechanical waves, and these are of two types. One is transverse wave, the other one is longitudinal waves. So what are transverse waves? So the waves formed on a string, they are transverse waves. Okay, So suppose this is a string, then one end of the string is connected to a rigid support, or you can say you have very rigid friend and he or she is holding that one end and other end is in your hand, okay, and you make it oscillate. The other end you are oscillating like this up and down. Then what will happen? The particles at this place will oscillate. Then because the string in the string the particles are connected to each other, if you make this particle oscillate, it will pull another particle, a nearby particle, right? So if this one is going up, then the particle at this end it's moving up, then it will pull a nearby particle too, so it will be also pulled up, okay. Then it will pull nearby particle, so it will be also pulled up. So in this way what happens, the wave travels along, right? So you are not moving this particle or this end only upwards, you are oscillating it up and down, okay. So this particle oscillates up and down, so nearby particle will also oscillate up and down, but then it will oscillate after a little bit of time, you can say, okay, after a very short time. And that's why if you see the displacement of this particle, displacement of the next particle, they will not be in phase. So if this particle moves up to this position, let's say, or in this wave, we can see this particle is at this point, okay. So it's oscillating like this. At the moment it is at this point. Next particle, it's not quite there, it is at this point. Next one has not reached that extreme position, okay. It is off by this much margin, let's say, or this much displacement, okay. So because of this there would be some phase difference. All particles are oscillating, but there would be some phase difference between particles, simply because there would be some time taken by energy to reach from this particle to this particle, or this particle will take some time to influence the next particle, that will take some time to influence the next particle, and that's why the oscillations are not in phase, and this thing gives rise to a wave, okay. Is this thing clear? Yes, no? Right. So this is a transverse wave. Then what is a longitudinal wave? So just for an example, this is a slinky, or you can take example of a spring, very long spring, okay. You pull its one end and you release it, then what will happen? So there would be oscillations along the length of spring, okay. So this end will oscillate like this, but then the next, so suppose this ring, okay, it will oscillate, but then this oscillation energy, it is carried to the next ring also, then it is carried to next ring, but it takes some time. So they will oscillate like this. The oscillations will not be in phase, okay, and it gives rise to this kind of a wave, right? So what is a wave? Wave is actually the oscillations of particles of medium, okay, but oscillations are not in phase. So different particles are oscillating with different phases, okay, right. So a wave in which oscillation of medium are parallel to direction of propagation, it is known as a longitudinal wave. And what is a transverse wave? A wave in which oscillations of medium or particles of medium is perpendicular to direction of propagation. So that is a transverse wave, right? So these are two types based upon the direction of oscillation and direction of propagation. Propagation means traveling, okay. So if wave is traveling this way and particles are oscillating perpendicular to that, it is a transverse wave. Wave travels this way, particles are also oscillating parallel to that, parallel to the direction of propagation, okay, parallel to direction of traveling, then it is known as a longitudinal wave, okay, very simple, right? And okay, so transverse waves can travel through solids, or they can travel along the boundary of two media. So they cannot travel through liquids, they cannot travel through gases, okay. Just remember this, transverse waves can travel through solids or along the boundary of two media, okay. And longitudinal waves, they can travel through solids, liquids as well as gases. Okay, longitudinal waves can travel through solids, liquids and as well as gases, right? Okay, so now here see, this is the propagation of sound, you can say. So here you have the speaker and there will be a diaphragm of speaker, okay, that will move inwards and outwards, okay, when speaker is played. So then what happens when it moves outwards, then it pushes the air near to it outwards, okay, and because of that what will happen, the particles of air or air particles, they will come closer to each other, okay. Then when it moves inwards, then what will happen, these particles will get time to expand, okay. So when particles come close to each other, that thing is known as compression. When particles go away from each other, that thing is known as rarefaction, okay. So in compression what happens, density of medium increases in that part, in rarefaction density decreases. So you can imagine if this medium oscillates like this, okay, then what will happen, the compressions and rarefactions will be formed periodically, okay, compressions and rarefactions will be formed, okay. So basically what happens is, these particles, they are pushed outwards, they collide on particles next to them, okay, they collide and come back like this, a lot of collisions will happen, okay. So they will collide and then these particles next to them, they are pushed in forward direction, these particles, they will move backwards, okay. So these particles, they will collide on particles next to them, right. So in this way the sound energy, it is carried. So this thing is clear, everyone, right? Okay, good. So these are compressions and rarefactions. So what are compressions? The high density region of space where the wave is traveling, and rarefactions are low density regions. Okay, so next very important point as far as NEET is concerned, equation of waves. Okay, so let's talk about this. So suppose you oscillate the string, okay, so you disturb the string, let's say disturb the string, so that means you just pull it like this, okay, you give one jerk and just keep it as it is. So then this crust is formed at this left end and it travels along the string, okay, crust is formed at left end and it travels along the string. So then now this disturbance, let's call it disturbance, it's originated at x equal to 0, okay, at t equal to 0, or let's say at x naught at t equal to 0, and in time t it reaches position x, okay. So now this is the disturbance, okay. So it is traveling with speed v, suppose v is the speed of wave, so it originates at x naught at time t equal to 0. Then after some time it reaches position x, okay. So let f is the function which gives the height of disturbance, okay. So f would be what, it would be function of position and time, okay. F is what, it is a function which gives height of this disturbance, so it will be function of what, position and time, because at this position the height is something at some time, but then it will change. So as wave moves from here to here, let's say, so then if you think about this position, then this point, this particle at this position, it was lifted by height h, but then after time t the wave has moved, so its displacement would change, right? Okay, so this would be height h prime, okay. So this has to be, the equation of wave has to be a function of position and time, right? Two things. Then you have, see, whatever is the value of this function, okay, whatever is value of this function at time x naught, sorry, at position x naught and time t equal to 0, okay, same would be the value of this function, right? Because height is given by this function f, okay, whatever is its value at this position at time t equal to 0, same would be its value at position x at time t, at time equal to t. Okay, so f of x and t is equal to f of x naught at time t equal to 0. Okay, so then you have displacement between these two. Okay, so wave is displaced from x naught to x. What is the displacement? X minus x naught, and you can always write that displacement is equal to vt, speed multiplied by time, right? Vt is equal to x minus x naught. Okay, or you can say x naught is equal to x minus vt. Okay, what is x naught? It is x minus vt. So here f of xt can be written as f of, in place of x naught I can write x minus vt, right, at t equal to 0. So f of x and t can be written as what? F of, in place of x naught I will write x minus vt, and in place of time I will just substitute 0 because the wave originated at t equal to 0. Okay, so it tells us that this wave must be a function of x minus vt. Okay, both dependencies on the position as well as time come in this one. Is this thing clear to everyone? So then f can be any legitimate function. So equation of wave which is traveling in positive x direction. So see, this one was a wave traveling in positive x direction. There we had f of x minus vt. So suppose the height is denoted by y. Okay, so y would be f of x minus vt if the wave is traveling in positive x direction, and y would be x plus vt if the wave is traveling in negative x direction, right? Traveling wave is also called as a progressive wave. Okay, because it progresses in some direction, and if this f is represented by a sine or cosine, which we are going to do, okay, then the wave is known as a simple harmonic progressive wave. Progressive because it is traveling. Okay, and why simple harmonic? Because we have seen in the last chapter simple harmonic motion, right? So simple harmonic motion is oscillations. So particles are oscillating, then this f would be what? Sine or cosine. Okay, right? Sine or cosine. Okay, and sine or cosine, they are called as harmonic functions. So therefore the wave is called as simple harmonic progressive wave, because when this wave travels in the medium, the particles of medium are performing simple harmonic motion. Okay, that's very simple, right? This is clear, everyone? So now let's talk about the equation of a simple harmonic progressive wave. So one equation, see, y is equal to a sine of some k multiplied by x minus vt. Okay, k is some constant. We'll talk about what constant it is. But now see, we have this function f. Okay, so f is suppose sine function, and sine will have maximum value of 1, right? So to represent the amplitude, we multiply the sine function with a. So a represents the amplitude of wave, because every time the amplitude will not be equal to 1, right? Amplitude will be different. So y is equal to some amplitude multiplied by sine of k times x minus vt. Okay, k is some constant, right? So then see, the wave will look like this. Okay, and this wave motion is doubly periodic. So it is doubly periodic means it is periodic in space as well as it is periodic in time. Okay, so what does that mean? So particle at this place, it will repeats its motion after time interval of t. Okay, and in that time interval the wave would reach up to a distance called as wavelength, and you can see that the displacement of this particle and displacement which is displacement of particle which is separated by wavelength lambda, it will be same. So this particle and this particle, they will oscillate up and down at the same time. Okay, so their phase is same. They will oscillate simultaneously, you can say, or in the same phase, up and down. So their displacement at a given time would be equal. Okay, once the wave reaches that point, right? Because if wave starts at this point, then only this particle will displace. Okay, it will be only after time equal to t the wave will reach at that point. Okay, then this particle and this particle will oscillate, okay, by equal distance, or oscillate, and their displacement will be same at the same time. This thing is clear, everyone? So suppose t is the time period of oscillation of particles and lambda is the distance covered by wave in time equal to capital T. Okay, so when one particle completes one oscillation, then the wave will reach up to this much distance. Okay, so this distance is known as wavelength. So it is distance covered by wave in time equal to capital T, and v is suppose the speed. Then what we can say, v is equal to distance covered divided by time taken. So v is equal to lambda by t. Okay, v is equal to lambda divided by t. And you know 1 by t is what? It's the frequency. 1 by t is frequency of oscillations. So therefore you can say v is equal to n times of lambda, right? So 1 by t is equal to frequency means n. So v is equal to n lambda, and you know this equation. Okay, so v is equal to n lambda. After that, now let's talk about the equation of this progressive wave. So we started with this equation, y is equal to a sine of k times x minus vt. Okay, and v can be written as, v can be written as what? Lambda by t. So you can put v is equal to lambda by t there. So you get a sine of k times x minus lambda by capital T into t. Okay, or lambda t by t, lambda small t by capital T. Okay, so now you take x is equal to 0. Okay, at position x equal to 0. Okay, so now you have y at t equal to 0 is equal to y at t equal to capital T, right? Because this particle at t equal to 0, suppose it's at origin. Okay, this particle is at origin. Now it will come back to the same position after time capital T. Okay, and therefore this thing is clear. But what would be its phase? So at t equal to 0, suppose phase is equal to 0. Okay, put t equal to 0. So what will you get? This is sine of x is 0, t is also 0. So phase is 0. So now as t increases, the phase changes, right? T increases, the phase changes. So you know sine of 0 is 0, sine of 360 degrees is 0, that is sine of 2 pi is 0. So what would be phase at t equals to capital T? The phase would be equal to 2 pi, right? The phase would be equal to 2 pi. Okay, so that means that this lambda small t by capital T at t equals to capital T would be equal to 2 pi. Okay, this thing is clear? Yes, no? X is 0. Okay, so what remains is lambda small t by capital T. So at t equal to capital T, the phase will be equal to 2 pi, right? So then at t equal to capital T, if phase becomes 2 pi, so at position x equal to 0, what is there? Only lambda small t by capital T. So that thing becomes 2 pi. Okay, so you have k times lambda small t by capital T, and at t equal to capital T, this becomes 2 pi. So you substitute t equals to capital T, so that t will get cancelled and you will get 2 pi. Okay, and then what you get is, you get k is equal to what? 2 pi divided by lambda. Okay, then you get k is equal to 2 pi divided by lambda, right? And then you substitute that back in this equation here. So if you substitute that, then what will you get? Okay, so here see, we substitute, we multiply this equation by k. So you will get y is equal to a sine of kx minus k times of lambda small t by capital T, and here we will substitute k is equal to 2 pi divided by lambda. So if you substitute that, this lambda and lambda will get cancelled, and what remains is, see, a sine of kx minus 2 pi small t by capital T, and what is that? 2 pi divided by capital T, it's equal to omega, and that's why you get this another equation, y is equal to a sine of kx minus omega t. Okay, you get another equation, y is equal to a sine of kx minus omega t, and this k is called as wave number. Okay, this one is called as what? Wave number. Okay, so this is equation of a simple harmonic progressive wave in another form, right? So this thing is clear? Yes, no? This is one form, this is another form. Okay, then there are various forms of this equation. So we can start with this form, y is equal to a sine of kx minus omega t. Then we can make use of k is equal to 2 pi by lambda, and we know this omega is equal to 2 pi by t, okay, from the last chapter, right? So then you can substitute k is equal to 2 pi by lambda in this equation, and omega is equal to 2 pi by t. So then you get y is equal to a sine of 2 pi x by lambda minus 2 pi small t by capital T. Okay, so that is another form. Then you can take 2 pi common, and you know then y would be equal to what? A sine of 2 pi x by lambda minus t by capital T. This is another form. Then the next one is y is equal to a sine of 2 pi x by lambda minus nt. Okay, this is another form, right? Then what else can you do? You can take this lambda out. So if you take lambda out, then you get y is equal to a sine of 2 pi by lambda, which is k, okay, multiplied by x minus. So you took lambda out, but there was no lambda here. So if you take lambda from the denominator, that means you will need to multiply numerator by lambda. So that is minus n times lambda t. Okay, and what is n times lambda? So n times lambda is v, and therefore you get y is equal to a sine of k times x minus vt. Okay, so these are different forms of this wave equation. There have been questions where this form or this form was used. So if you remember this form, then you can solve the question directly. Okay, or even if you don't remember, then converting from this one to this one or converting from this one to this one is very simple. You just need to remember this, that k is equal to what? 2 pi by lambda, and omega is 2 pi by t, right? This thing is clear. Okay, everyone? All right. So there have been questions based on this form and this form also. Okay, this form is actually most important, we can say. Okay, but then if you remember this and this as well, this equation and this equation as well, then the question, so this will be direct formula for the question. Otherwise you will need to come from this form to this form. Okay, and that's not difficult, right? All right, so now see this next equation, y is equal to a sine of omega t minus kx. Okay, y is equal to a sine of omega t minus kx. So if you see this equation, in what direction is this wave traveling? So first of all, is it a wave? It's a wave, right? Because there is kx, there is omega t. Okay, so either it is kx plus omega t, kx minus omega t, or it is omega t minus kx, right? So function of these things are waves. So this is omega t minus kx. So can you tell me in what direction is this wave traveling? In what direction is this wave traveling? Positive x direction, right? It is traveling in positive x direction, everyone. Okay, right? So we can see it here. So see, this is a sine of omega t minus kx. Okay, and then you can take this negative sign outside, because you know sine of minus theta is equal to minus sine theta. Okay, so I can just take negative sign outside, and then what I will get is sine of kx minus omega t. Okay, so if I just move negative sign outside, I will get minus sine of kx minus omega t, right? So then this minus a can be written as some b. Okay, right, minus a can be written as b. So then what you get is y is equal to b sine of kx minus omega t. So of course, this is a wave traveling in positive x direction. So this is still a wave traveling in positive x direction only, right? This is a wave traveling in positive x direction only. So whether it is kx minus omega t minus kx, it is a wave traveling in positive x direction. Okay. So you remember it this way: if the sign of the x term and t term is not equal, then the wave is traveling in positive direction. Okay. X term, or you can say position term. So sometimes there would be y also. Sometimes they can write it as z. Okay. So sign of position term and the time term, if it is not equal, then it travels in positive direction. If it is equal, then it travels in negative direction. Okay. So if it is omega t plus kx or minus omega t minus kx, they are traveling in negative x direction. Right? This is clear, everyone? Okay. Is there any question based on this? Is there any doubt on this? All right. So that thing I have written explicitly here. Right. So then let's next see the path difference and phase difference. Okay. So theta is suppose the phase difference and x is the path difference. So what is path difference? So suppose you have 2 points separated by some distance. 2 points of the medium, they are separated by distance x. Okay. 2 points of the medium, they are separated by distance x. And theta is phase difference between them. Okay. What is theta? Theta is the phase difference between them. Okay. So then this theta must be directly proportional to x. Okay. Theta is the phase difference. It must be directly proportional to x because the wave is traveling with a constant speed, right? So we can write that theta is equal to some constant c times x. Okay. And then when you have x equal to lambda, theta is equal to 2 pi, right? If path difference is equal to lambda, okay, here you can think about it in this way: the wave moves from here to here. Okay. So phase of this particle at this moment is equal to 0 because wave have just come to this, wave has just reached this position. So phase of this particle is equal to 0. But what about the phase of first particle or the particle at the start? The phase of this particle would be 2 pi because it has completed one oscillation, right? So how much is the phase difference between these two particles? Phase difference is 2 pi. Phase, the wave suppose originates at this point. When it reaches this point, then what will happen? The phase of this particle is equal to 0 suppose, because wave has just arrived at this particle, okay, this point. So this particle has not started oscillation, okay, it is going to start now, just now, okay, and then at this point this particle has completed one oscillation, then only the wave will reach this point. Okay, so one oscillation is completed means its phase has changed by 2 pi. Okay, so how much is phase difference? If particles are separated by lambda, then phase difference is equal to 2 pi. This thing is clear, everyone? Yes, no? Particles are separated by lambda, phase difference is equal to 2 pi. Okay, so then we can write 2 pi is equal to that constant c times lambda, and if phase difference is theta, okay, if particles are separated by x, suppose the phase difference is theta, then theta is equal to c times x, means if particles are separated by lambda, phase difference is 2 pi, then you will get 2 pi equals to c times lambda. So you can just divide this equation by that equation, okay, or you can say this is first, this is second, divide first by second, then what will you get? Okay, if you divide first by second, then you will get theta upon 2 pi is equal to x by lambda, right? And you can move that 2 pi on other side, then you get theta is equal to 2 pi x by lambda. Okay, and then you know what is 2 pi by lambda? it is wave number, okay, it is k, right? So theta is equal to 2 pi x by lambda. So phase difference, if part difference is x, phase difference is theta, what's the relation between them? Theta is equal to 2 pi x by lambda. Okay, this thing is clear, everyone? We need to remember this formula, right? If phase difference is theta and part difference is x, what's the relation between them? Theta is equal to 2 pi x by lambda. Okay. All right. So now let us see some problems based upon this thing. Okay. So we have seen very basic things, right? So which one of the following statements is true? Tell me, both light and sound waves can travel in vacuum. Can sound waves travel in vacuum? Can sound waves travel in vacuum? No, they can't travel. Okay, sound waves are mechanical waves, right? They can travel in solid, liquid gases, but not in vacuum. All right, both light and sound waves in air are transverse. So sound is compressions and rarefactions. They are longitudinal waves, right? Sound waves in air are longitudinal, while the light waves are transverse. Is this one correct? This one is correct, right? That's too basic, but it was asked. Okay, sound waves are longitudinal and light waves are transverse. Okay, this is clear. All right, let's see next one. With the propagation of longitudinal waves through a material medium, the quantities transmitted in propagation direction are energy, momentum and mass, energy and mass, energy and linear momentum. Tell me. Momentum is also carried, no? Otherwise, how will the particles move? Right? You can think in terms of longitudinal wave. So one particle pushes another particle, that particle pushes the next particle, that one pushes the next particle. So energy is carried as well as the particles are moving. So momentum is also carried, right? So the answer is option D. Mass is not carried. Okay. Why is it not carried? Because particles are not moving from one place to another place. Okay. They are just oscillating about the mean position. Even in case of a longitudinal wave, the particles will oscillate at the mean position. But while this particle oscillates, it collides with another particles and it will also oscillate. Okay, the next particle will also oscillate because of collision with this one, right? So particles are not traveling, wave is moving, means these particles, these oscillating particles, they make the nearby particles oscillate. They make nearby particles oscillate. In this way, the wave is traveling. Okay, so it is energy and linear momentum only and not the mass, right? Very, very basic question, but still it can be asked. Two waves are represented by equations. This is first wave and this is second wave, where x is in meter and t in second. The phase difference between them is, okay. So this is just a comparison now. So y1 is equal to, you have a sine of omega t plus kx plus 0.57. So this is the phase of first one, right? This is the phase of first one. Y2 is equal to a cos of omega t plus kx, and then we know cos theta is equal to what? Because first one is written in terms of sine. So you have sine of theta plus pi by 2 or pi by 2 plus theta is cos of theta, right? So this one is a times sine of omega t plus kx plus pi by 2, right? And then if you compare them, so this term is common. So this is suppose phi 1 and this is phi 2, right? This term is phi 2. So what is phi 2 minus phi 1? So phi 2 minus phi 1 is the phase difference. Okay, phase difference is phi 2 minus phi 1, and that is just equal to pi by 2 minus 0.57. It's very simple. Pi by 2 minus 0.57. So that is 3.14. 3.14 divided by 2 minus 0.57, and I guess this is 1.57. Okay, 1.57 minus 0.7, 0.57, it is 1, right? So answer is 1, option A. This is very simple. Let's see the next question. A wave traveling in positive x direction having displacement along y direction as 1 meter, wavelength 2 pi meter, and frequency of 1 by pi hertz is represented by. So you have a wave traveling in positive x direction and its displacement along y direction is 1 meter. So they are talking about the amplitude here. So amplitude is 1 meter. Okay. So then wavelength is lambda is 2 pi. So lambda is 2 pi, and frequency, so n is equal to 1 by pi. So then make use of any equation, right? Y is equal to what? A sine of, you have kx minus omega t, right? So that is equal to A sine of k is 2 pi by lambda, 2 pi by lambda times x minus omega is 2 pi n. So you have 2 pi nt, and that is equal to A is 1, and then you have sine of 2 pi by lambda, lambda is also 2 pi, so 2 pi by 2 pi times x minus you have 2 pi, okay, and n is 1 by pi, right? So it is 1 by pi times t, so that pi gets cancelled and this 2 pi gets cancelled. The equation is sine of x minus 2t, right? So it is option C. Okay, so this is clear. Okay, good. Let's see next one. A wave in a string has an amplitude of 2 centimeters. The wave travels in positive direction of x-axis with speed of 128 meters per second, and it is noted that 5 complete waves fit in 4 meter length of the string. So 5 complete waves fit in 4 meter length. Okay, the equation describing the wave is, so if 5 waves fit in 4 meter length, so that means you have 5 lambda equals to 4 meters. So therefore you have lambda equals to what? 4 by 5. Okay, 4 by 5 meters. And then you have speed is equal to 128 and the amplitude is 2 centimeters. So amplitude is 0.02 meters. Okay, and what is speed? Speed is 128 meters per second. Okay, then you know speed is v is equal to n lambda, right? So then you have n is equal to what? V by lambda, and that is 128 divided by lambda is 4 by 5. Then what is 128 divided by 4? So I guess it is 32. 32 times 5. So this is 160. So 160 hertz. So frequency is 160 hertz. And then you can make use of any equation. Okay, equation of a wave. Y is equal to, you have A sine of kx, which is 2 pi x by lambda. Okay, minus it is 2 pi nt. Okay, y is equal to A sine of kx minus omega t, but because it is all solved over here, so we are making use of this one. Okay, so we are writing k as 2 pi by lambda and omega as 2 pi n, right? So then put the values. A multiplied by sine of, it is 2 pi divided by, so 2 pi is 2 multiplied by what? 3.14. So 6.28 divided by lambda is 4 by 5. Okay, so it's 0.8 times x minus 2 pi. So 6.28 times n is 160. Okay, times t. All right, so it is 160 times 6.28, right? So 16 6 are 96. So close to 100, 100 and then there is this 0, so 1000, it will be close to 1000. Okay, so it's either option C or option D, but there is this negative sign here. Okay, and I guess this thing would be equal to what? 7.85. Okay, so then this negative sign is there, that means it is option C. Okay, A 0.02 multiplied by sine of, you have 7.85x minus 1005 t. Okay, I think it is option C, right? Yes, no? Okay, then let's see next one. The wave described by y is equal to 0.25 sine of 10 pi x minus 2 pi t, where x and y are in meters and t in second, is wave traveling along the. Okay, so there is negative sign, so the position and time terms, they have unequal sign. That means it is traveling in positive x direction. Okay, positive x direction, right? And then positive x direction, so it's option A or option D. But then they say the frequency is 1 hertz and wavelength is 0.2 meters. Frequency is pi hertz and wavelength is 0.2. So wavelength is same here. That means you need to check the frequency, right? So either option A or D. So let's check the frequency. So here comparing with y is equal to A sine of 2 pi x by lambda, or you can say just kx minus, because we want to compare this term only, kx minus omega t, that is 2 pi nt. Okay, you have 2 pi n is equal to 2 pi. Oh, so 2 pi n is equal to 2 pi, means n is equal to 1 only, right? N is equal to 1, right? So therefore it is option A. Okay, this is clear.